The fountain of youth, sometimes known as Aqua de Vida, was a legendary spring that restored youth or granted immortality from anybody that drank from its waters. Are you guys offering us a little drink?
Yeah.
It would be a little bit of a drink for your knees, but yes, that's essentially what we're trying to do here. Specialized types of cells in the body. They are essentially the fountain of youth.
Hi everyone, and welcome to this edition of Backstory. I'm Dana Lewis. From London, I want to share with you what could be a bit of magic if you're a runner, or just aging and you need hip surgery, shoulder problems, knees are wearing out. Listen, let's talk about stem cells. Definition: they are capable of giving rise to indefinitely more cells of the same type. Translation: those magic cells in your body that make you grow things like cartilage. But that wears away as you get older. I'm missing some cartilage in my knee. And since the COVID-19 pandemic began, I don't miss a day running. But my knees hurt. And I've had 2 operations over the year to clean up my knee. And the cartilage is wearing thin in my knee joints. In fact, almost everyone suffers the same problem as they age, especially if you do a lot of sports. Tennis, rugby, hockey. You probably suffer some knee problem. Are you ready for some earth-shaking health news? What if there was a way to reverse aging and make cartilage regrow by stimulating stem cells? Well, a new study out of Stanford School of Medicine has succeeded in doing exactly that. I want to run a marathon. Maybe you do too. Listen to this backstory. It's very promising news. All right, I want to introduce you to the 2 people who put most of this research together, and we'll walk through it with them. First of all is Dr. Matthew Murphy.
Hello, pleasure to be here.
And then we take you all the way into another time zone. It sounds like the Twilight Zone, but it's Chuck Chan is speaking to us. He is an assistant professor at Stanford, but he's in the Palo Alto, California campus. Hi, Chuck.
Hi, Dana. Thanks a lot for the opportunity to be here.
It's great to talk to you both. The fountain of youth, sometimes known as Aqua de Vida, was a legendary spring that restored youth or granted immortality from anybody that drank from its waters. Are you guys offering us a little drink?
Yeah.
It would be a little bit of a drink for your knees, but yes, that's essentially what we're trying to do here.
All right. This is really exciting because I don't think people realize how many people, as they get older, and I'm an older runner, I will confess, I know I don't look that way, but I don't think people realize, 1 in 10 people by the time they're 80 has had a hip replacement. 1 in 10, and it may be even higher than that, has had a knee replacement. And what you've done in your research is, I'm told, is that you are finding a way to regrow cartilage. So who wants to take the first run of this? Matthew, Dr. Murphy, do you want to explain what you've done?
Sure, no problem at all. Well, my background is I did medicine at University College Dublin. And while I was over there, I really focused on hand surgery. And we applied a principle known as microfracture to the joints of the base of the thumb, which was new at that time. However, microfracture to the knee, as you might know, anyone who's an avid sports person who might have had microfracture surgery, has been around since the 1960s. We thought, and it has always been believed, that by microfracturing, you're able to somehow rejuvenate the joint by forming a scarred tissue known as fibrocartilage. However, the positive effects seen by microfracture often wear away with time. So I wanted to find out, and in order to do this, we had to really go down to the very basics behind it, the purest form of science, to look at it at a cellular level. And Professor Charles Chan at Stanford had found the mouse skeletal stem cell and subsequently the human skeletal stem cell. So in order to see, first of all, does microfracture even activate these cells, we had to try it first on isolating these specific cells from the joints of mice and then in human tissues as well. So it was really important to see that skeletal stem cells exist in mouse and human tissue, like old arthritic knees.
Will you take me back? Will you, just before we go on with that, will you take me back and Chuck, if you want to do this, when you are young,
Sure.
You have stem cells that grow things like cartilage between your knees.
Yes.
which acts as as that shock absorber between the knees. And then suddenly I'm told around 14, 15, 17, your body kind of turns it off. Is that accurate?
That's correct. So, as Matthew explained, normally we have these specialized types of cells in the body. They are essentially the fountain of youth. But for every single different types of tissues, there is a different fountain of youth. You can think of it as a fountain of youth because this is where new tissues come from. These are the cells that forms new tissues. They have the ability to make different types of tissues, and they also have the ability to make more of themselves. During development, these are the cell types that are responsible for making the majority of the tissues as the organism grows. And so there are skeletal stem cells normally early on in the joints that is responsible for forming the cartilage. However, unlike bones, which these stem cells also form, and which has the ability to regenerate, adult cartilage has practically zero regenerative ability.
Tragically so. Because as you get older, you inevitably wear out that cartilage between your knees, or you wear it out in other parts of your body.
Yes. And unfortunately, the more active you are, in some people, then it wears out even faster. So this is due to the fact that at least we thought that there was a change in stem cell activity during aging. And we thought that
translation, you just stop making stem cells, right?
That's right. The fountain of youth has been turned off.
Okay.
But what we found was actually that is not entirely the case, that there were still skeletal stem cells residing within the cartilage and the underlying bone.
All right. And that's where we go back then. Before I interrupted you, that's where we go back to, you were able to activate that.
That's right. They're simply quiescent. They're asleep, basically.
Dr.
And
Murphy,
in the response
will you lead me through then the injury that you did to bone in mice to begin with, about how you're able to activate that?
So we tried to replicate or try to imitate what commonly is performed by orthopedic surgeons. So frequently any microfracture surgery results in the formation of fibrocartilage. And how it does that is you debride off the diseased cartilage first, and you make small holes into the underlying subchondral, which means under the cartilage bone. And frequently orthopedic surgeons do that using trocars. However, there's been new studies that show...
What's that mean?
Trocars are like pointy needles that they use to poke holes down through, and the result leads to like a blood clot that forms within the area that you've debrided, and this then forms fibrocartilage. But there's studies that show that using a trocar, or like a pointy needle, doesn't have as good effect as if you use a micro drill, because it's actually using a micro drill, a very small drill, the same size, the same diameter as the needle, actually allows you to maintain the architecture of the subchondral bony space. And this allows for better activation of those stem cells.
Okay. Now, after 2 operations on my knee and people telling me, you should just go get knee replacement because your knees are shot, your cartilage is never going to come back, I did have stem cell. And they told me that it might help you with inflammation, but it wouldn't regrow cartilage. And then I had somebody else saying, well, yeah, it might regrow a cartilage. And they were, probably judged by most professional surgeons as false promises and smoke and mirrors. So now I've been holding back on any kind of knee replacement because I think that eventually we'll turn the corner on stem cell, and brilliant people like you will be able to lead us to the point where we can regrow cartilage. And a lot of people are saying that's snake oil. Now, are you telling me we've arrived at that corner? We're turning that now? This
is the first time that we've actually seen, and other investigators have reported, formation of this so-called hyaline cartilage. We've been talking about different types of cartilage during this interview. There's the fibrocartilage. Although it sounds like it is the same type of material as normal cartilage in the joint, it's not. it's more of a scar tissue that's made of a fibrous capsule. And it's better than bone rubbing against bone. It forms a sort of a Band-Aid over the injured area, but it doesn't have the same mechanical properties as true cartilage, what we refer to as hyaline cartilage. So what we have managed to do in this process is form true durable hyaline cartilage from these skeletal stem cells. And the way that Matthew discovered that this happens is that these skeletal stem cells that he can awaken through the surgical procedure of microfracture normally has the option to turn not only into fibrous fibrocartilage or scar cartilage, which is not really true cartilage, but also bone as well as true hyaline cartilage.
This was in mice.
This is in mice and also in human joint tissue that we have grown on the backs of mice. So we would take some of these tissues from a patient and then grow it in a mouse by attaching it to a blood supply. And so these would be viable human tissue growing on the back of a mouse. And that was in order for us to test whether or not this combination of factors that we use to coach these awakened stem cells towards true cartilage also functions in human tissues rather than only in mouse tissues.
So Matthew, can you give me some perspective on, is this just like, minute amounts, or do you think that you could actually stimulate enough to replace this damaged cartilage in the knee? For instance, I know there are other joints that we're talking about, but I'm selfishly talking about knees too much today.
No, there certainly is the potential to be able to use it for larger joints. However, it's very important that we take our findings with an element of really making sure that we do rigorous tests before we try anything too quickly. And so it's important that we ensure we've shown these results in smaller mammals. It's important then to take it to larger animal studies and subsequently then move it towards human studies in a controlled environment where we know specifically what's happening to the cells. As you mentioned before, yes, other groups have mentioned that they have stem cells, and stem cells is a very cool topic, and it is this, I think you used the word snake oil. I'm not sure exactly what that means.
Snake oil's when those guys used to go around in the old Western movies, and they used to appear in the town square, and they'd be selling some kind of snake oil, and they'd say it was a cure-all, and it would solve all of your ills, right? And it was probably just some water with some dye in it. So and actually, it's a very old term, but when I saw a doctor in England about my knee in London, he said, don't believe any of the stem cell stuff. It's just snake oil. And the balloon went poof for me, because I thought, wow, if we can get to stem cell regrowth, how incredible that would be for so many people.
And I think when you mentioned, are we turning the corner? I think we are, because groups like Professor Chan's in Stanford have the ability now to more accurately hone in on the specific cells, and therefore we can see the effects of what we do mechanically, chemically, how we alter the environment, how that would affect those stem cells. Whereas before, we had less ability through technologies that were more limited, that we couldn't identify specific cells, or at least more specific subtypes of cells. And so therefore they were all grouped. Often a lot of it's like, finding the new world and labeling new countries and things. People have a habit of sometimes over-promising and over-labeling, but not to sound like a pessimist, it's important to take it step by step and to be cautious with our findings and not over-promise too many things. But I think, as you say yourself, I think technology has allowed us to now move forward in a more controlled and more specific way, that we can really accurately predict how these cells might act in a controlled environment.
Chuck, what was that novel of Mice and Men, or if I recall my high school reading, mice are not men, or women for that matter. Do you think that you can go to larger mammals and then human testing, and that this will hold up?
I think that's the hope. The factors that we use in this study, that one of the things that was exciting about it was that they are already FDA approved in the US for use in humans. So one of these factors, it's called BMP2, and it's also marketed as Infuse. And this is a product that's normally used to fuse bones during spinal fusion. So that's a chemical that's already been used in humans, and its properties are somewhat well known. And then the other drug is a product that's similar to Avastin, and that's an anti-cancer drug that blocks a certain type of blood vessel forming cell signaling.
And what do these two drugs do that when you're doing the small fractures? Is that when you use them?
That's right. So the unusual thing about these signals is that you can think of them as letters in a word. They're kind of an alphabet. And if you rearrange these signals a different way for a different type of cells, it means a completely different thing, for instance, than what it would mean for a cancer cell. If you combine these two factors together for the joint, it means two things. First, make more of the stem cells. So that's what the BMP does. It expands the stem cells. And then second, the anti-VEGF, which normally means tells tissues not to make blood vessels. Instead, it tells these amplified skeletal stem cells not to make bone or fibroblasts. And when these two options are shut off, then the stem cells turns into the default state, which is cartilage.
Really?
That's right. So make more stem cells.
Really exciting.
And don't make bone or scar tissue, and you'll make cartilage.
So do you think you could make enough in humans to replace cartilage?
In the case of the mice, when we deliver these factors in using this material, we were able to resurface most of the entire joint.
Wow.
So if we were able to scale this approach appropriately, then there's that possibility. But as Matthew pointed out, right now, one thing that we're concerned about is potentially surgeons trying to use these drugs on their own, which are already out in the market, and getting undesirable results. Because what we have observed is that the concentration and the timing of these factors are very important. There's another aspect to this that we're still working on, which is the shape of the new cartilage that's formed. So
because it's got to be the right shape.
That's right. And so what we're afraid of is that if you were just to inject these two factors without the proper material to give them the right shape, you will have cartilage that doesn't really conform to the appropriate
joint,
contours. That's right. That's right. So it just wouldn't be the right shape. So that's something that we have to work on next in larger animals.
Larger animals. And then Matthew, how soon could this go to human testing then?
Well, I know that certainly the factors are very close they are FDA approved, as Professor Chan has already mentioned. And so I think once we have confirmed it in larger animals and we can see that it's robust cartilage that's formed in those larger animals, then we'll be able to move forward in a controlled way. I would say that currently, you've mentioned knee arthritis, but there's also other forms of osteoarthritis that affect other joints. And at the moment, I'm currently an academic clinical fellow at the University of Manchester. And I've rotated through a hand rotation with Professor Lees and Mr. Mishra. And they have often looked at patients that suffer from quite severe arthritis of the base of thumb. And this is a particularly debilitating disease. And at the moment, the current treatment is to simply take out the affected bone. So they don't even replace it with anything like you would in a knee joint. You have your knee replacement. In the base of thumb, they simply take out the bone. So it's a pretty crude operation. So it would be great to see how these factors might work in a bone that we would otherwise be removing, because if there's a negative result, the end result would be that we would remove the bone anyway. So there's no real loss. And so this allows us more potential flexibility in transferring or translating this basic science finding into more clinically relevant findings.
So I think, yeah, absolutely. And obviously it's got to go forward in a reasonable way, right? But I think stem cell is probably one, and platelet, PRP is probably, these are some of the biggest rackets. That's my word. But yes. I know they take thousands of people. I was in a clinic in London, which I won't mention, said, give me 50,000 pounds your eyesight will improve, your skin will look 10 years younger, your liver and kidney functions will be different, your knee will regrow cartilage. And I said, seriously? This is a few years ago. And I said, will you show me the MRIs or show me some proof of other patients who's gone through that? And they said, well, because of patient confidentiality, we can't do it. And then eventually, I think the government of Canada stopped some of the stem cell injections that were going on because people have been promised the moon. Mm-hmm. Stem cell, obviously, while it's promising, it didn't produce. Right. So this is one of those cases. Are you worried that doctors now are going to pick up on some of this and just go and start trying to experiment with patients, or because there's drugs involved, maybe it's going to have to be a little more regulated?
Oh, will 100% have to be more regulated, and there will always be those so-called cowboys with snake oil that will be trying to sell you everything and more. But if it sounds too good to be true, it normally is too good to be true. And certainly coming at it from a more rigorous basic science approach, it takes a lot more time and a lot more thought before anyone with a conscience could really reliably tell you that it works well. And so it will take a few more years to come through. I mean, people might try and use those compounds, but to do so would be quite dangerous because even though we've seen a positive effect in smaller animals, I would be cautious. Having seen the great effect that it has, I would still be cautious moving forward with humans.
I know one of you drew an analogy to a Jiffy Lube model of cartilage replenishment.
Oh, yes.
Where was that you, Chuck? I don't know, but
So all of this work was done in collaboration with a mentor of mine, Mike Longacre.
Yes.
At Stanford University. He's the director of the regenerative medicine program there.
And the idea, also, the parallel with Jiffy Lube is you wouldn't necessarily go and do this treatment once, but you may do it sort of a regular cartilage replenishment.
That's right. So if we see that these two factors could stimulate cartilage regeneration, perhaps we can also try delivering it in the proper format, in the proper combinations, periodically before the cartilage has completely eroded away. And maybe we can see.
Does it matter if there's some cartilage there, or because if you can stimulate stem cell production, do you need old cartilage to bond to, or does it matter how far along the deterioration of cartilage is already?
I think it might matter to ensure that the new cartilage does bond with the old cartilage, and not just from the mechanical perspective of getting the joint to function properly and getting to the new cartilage to stay in place. However, we have seen that these factors can also restore cartilage, even though all the cartilage is gone, by directly growing new cartilage on top of the subchondral bones.
Well, you guys got to get going. I'm not getting any younger, and we need to get this done. So when do I sign up? I mean, what is the next big animal you go to before you come to humans?
There are certain types of animals, like sheep, for instance, and dogs that normally develops osteoarthritis.
Yeah.
And so what we would like to do is to perform a large animal study in various joints. We would try the joints of the toes, for instance, and also the knees, to try certain combinations of these factors to see if we can optimize the type of cartilage that's formed. That's probably going to take us around like 1 or 2 years.
Incredible. And so, and just to clarify, I understand as soon as you get an injury, you have inflammation, you have arthritis.
Yes.
But you may still have cartilage. But so does this help with arthritis?
It helps with the arthritis. It certainly helps with the pain. So I think Matthew can talk a little bit about how we showed that in mice.
So to get mice, to observe mice and see how they are responding to the treatment, you can actually, there's technology that allows you to look at how the mouse walks, and we describe that as the gait of the mouse. And so you can see if they have a limp, and you can see if their stride and where they're placing their weight on each of the feet. So it's a superb technology. However, again, looking at smaller animals, they're very different to larger animals. So smaller animals are known to be able to mask their pain quite well in a survival mechanism that prevents them. It's the fight or flight response that prevents them from being eaten by predators. So again, smaller animals are very different to larger animals, and we'll have to reassess that on the larger animals themselves. So I don't know if you have a golden Labrador, they'll probably be able to walk sooner, hopefully, than some lucky dogs with this treatment. We might see a good response with those, and then we can roll on with the human trials.
So it may reduce pain, it may reduce levels of arthritis. It's not going to reverse severely arthritic joints that are, completely locked up, though.
That's one thing that we're hoping that it actually might be able to do. We want to resurface the whole joint. And that actually depends on the utility of a procedure that is commonly used for treating joint injuries, and that's called arthroscopy. And so the surgeons, and these are performed many times a year. In the US, it's fairly routine. Their surgeon makes an incision on the knee and sticks a fiber optic cable within the knee. Now, you can do this for the joints, right? But you can't do this for a lot of other tissues, for instance, the brain. So this is a well-established technique. And so what we're thinking is that we will create a new type of scaffold that would allow you to deliver this material during an arthroscopic procedure. So you would go in, debride most of the missing pieces of cartilage or the free-floating bones, and then you would install this new material, and it would regrow some of the new cartilage, thereby at least perhaps even replacing the need for a joint replacement prosthesis to be installed.
Replacing the knee or just short-circuiting the need to replace it.
That's right, bypassing the need for a joint replacement.
That's why it's so promising. Chuck Chan, the assistant professor at Stanford, and Dr. Matthew Murphy, an amazing medical evolution. And a lot of what we have is pretty crude in terms of dealing with joint problems. And this is the future, and we're all hoping you guys do well, because then we're all going to be the benefactors of that. So thank you so much.
Thank you very much for this opportunity. And we'd like to also thank our supporters at the National Institute of Aging, the Arthritis National Research Foundation, and American Federation for Aging Research for supporting this work. Also, the California Institute for Regenerative Medicine. Because
there are tens of millions of dollars that is going into this area of research, right?
That's right.
So many people are affected by arthritis and bad joints.
Yes. So we're really, really grateful for the taxpayer support of this research of basic science.
Matthew, thank you.
Thank you very much. And I'd like to take this opportunity as well to thank you for your time, but also to thank my two mentors, Professor Chan and Professor Longacre, as well as my co-worker, Lauren Kopke, who did a lot of this fantastic work as well.
Exciting stuff.
It is. It's fantastic. Thank you very much for your time.
Thank you, guys. And that's this edition of Backstory on stem cells and the regrowth of cartilage. We are years away from this new medicine, but maybe only a few years. I want to run that marathon still, and I'll keep you up to date on Backstory as this progresses. It's fantastic medical science. I'm Dana Lewis, the host of Backstory. If you would like to become a sponsor of Backstory, get in touch. And please subscribe and share our podcast. I'm off for a run. I'll talk to you again soon.